We're going to go through those formulas again, those big 6 trigonometric formulas. These are referred to as the basic 6 trigonometric ratios. We're also going to work on some problems using these trigonometric ratios. Before I do so, let's remind ourselves of some things we discussed yesterday. First of all, some terminology. When it comes to these problems, these are going to be right triangle problems. So every triangle we're going to deal with is going to be a right triangle. In order to assist with this today, we're adding one more formula, Pythagorean's theorem. Now, fun mathematical fact, Pythagorean's theorem is debated to this day as to whether or not Pythagoras was a real person. This is mainly because there was actually a cult in ancient Greece referred to as the cult of Pythagoras, and so they are actually the ones commonly attributed to inventing this particular theorem. This is still disputed by some mathematicians. Some people still think they were real. Some people still think it was one person. It's one of the few debates that still goes on to this day. It's kind of fun, kind of interesting. If you want to look it up, it is more than worth the 5-minute Wikipedia article. Okay. One thing I would note, one change to Pythagorean's theorem that I would put on here, is that because of how we're going to be using notation in trigonometry, this is the alternative I would suggest, writing down for your notes. O squared plus A squared equals H squared. It's the same theorem, but it's written with the same letters we have for all of our pieces of a trigonometric function. We have opposite, adjacent, hypotenuse for all of our right triangles. So we note we have all of our components as O, A, and H in Pythagorean's theorem as well. This helps keep everything consistent and clean and feel less random and sporadic by having A, B, and C randomly thrown in there. Again, it's meant to be a way to keep track of your information better than just having 3 random letters for 2 different parts of the exact same problem. Now, those formulas, one more time. Listed as sine, cosine, and tangent, cosecant, secant, and cotangent. Each one represents a different relationship of the components of a triangle. Each one is related specifically to the angle in your triangle. In order to determine which trig function you're looking at and the value of that trigonometric ratio, you must have an angle that you are dictating the problem by, which we have called theta in these examples. But as we've seen already, we can call it x, we can call it alpha, we can call it beta, we can call it phi. There's a lot of different things we could call it. It's standard in trig to call it theta. Once you have dictated where theta is, we can dictate which sides are opposite and adjacent. The hypotenuse is fixed, so that's never a question. And with that, we can determine the trigonometric ratios. For the problems we're going to talk about today, you could, if you wished, construct these problems, like using a protractor or a piece of paper and a ruler. And you can construct them in such a way that you could verify these answers with a calculator if you actually wanted to. And that'll be one of the things I'll showcase tomorrow in our lesson, is that these theorems, these ideas, do fit together. So if you have a triangle that meets these very specific qualifications, when you type in sine of that angle, it will pop out with this fraction exactly the way it should. Same with cosine, tangent, and the other big 3. For today, let's think about our first problem. This will be the consistent way problems are written in this class for the next 2 days. Find the 6 trig ratios for the triangle and give an angle. Now, the only difference will be these ones will typically have some information given, such as this is a 3, 4, 5 triangle. Note this problem. What makes this a trig ratio problem is that the angle is unknown, meaning that the calculator is not required for the trig part of the problem. It is required to get the trig ratios correct. So in this problem, there's a specific order of operations when it comes to ratio questions. If you took the last 2 ACTs, either one of them, I believe each one contained at least one problem that dealt specifically with trigonometric ratios. These are actually much easier than you think.
Austin Reed, you're needed in the office. Austin Reed, you're needed in the office.
Because the goal of them is we don't need theta. We don't need a calculator to determine these ratios because the ratios are built by the angle and the specific sides of that triangle. So for example, in this picture, before I start on the actual trigonometric ratios, let's start by defining the sides we talked about yesterday. Opposite, adjacent, and hypotenuse. When I do these kinds of problems, my go-to is to start with the hypotenuse because it's the one that's consistently always the same. It is the longest side, it is across from the right angle. For this particular problem, which of my 3 sides should be my hypotenuse? The 5, yeah. So I'm going to label that with an H. Indicating this is in fact the hypotenuse. Now keep in mind, here is where theta is. So we now need to dictate the other 2 components, opposite, adjacent by its location of theta. If theta is in the upper right-hand corner, as it is here, which side is going to be my opposite side? The 4. Which would make the 3 the adjacent side. Now, let's talk about the trigonometric ratios. The problem actually asked about. This is all preliminary work. In order to determine trigonometric ratios, you must first have all 3 sides of a triangle with a labeled angle that you are dictating the ratios based upon. And then once you have all those pieces, they must be labeled as opposite, adjacent, and hypotenuse. That is because to determine things like sine, cosine, and tangent, you have to know which is which. Using my little cheat sheet over here as reference, let's talk about the trig ratios. Sine, cosine, and tangent. Now, the angle in question in this case is a theta, so I'll do sine of theta, cosine of theta, tangent of theta. Now again, a calculator is designed to find theta, specifically using the trigonometric ratios pre-programmed. We're going to ignore that for now. Instead, we're going to determine the ratios themselves. There is a way to work backwards to find theta using an inverse, but for now, let's focus upon identifying the relationships first. One more time. The 6 trigonometric functions just define a specific relationship between the sides of the triangles and a specific angle of that triangle. That's all they do. So as long as theta is this size and those sides are those sizes, these relationships can be proven with the calculator, with the protractor, with the ruler, and a piece of paper. Let's talk about each one. Sine. According to our cheat sheet, sine is equivalent to opposite over hypotenuse, so some old hippie. So I go to my list. For sine, we'd have opposite, which is 4, hypotenuse, which is 5. So the sine function would have a ratio of 4 over 5. This is your trigonometric ratio. And that's as simple as it gets. It's identifying which relationship exists for this particular triangle, for this particular angle, for this particular function. It sounds more complicated than it is. It's just an exercise in knowing how these pieces are supposed to fit together. Which means that in any 4, 3, 5 triangle, sine would always be the one that is 4 over 5 in this particular example. Cosine, same process. In this case, cosine is listed as adjacent over hypotenuse. Adjacent, 3, hypotenuse, 5. So 3 over 5 represents the cosine of this particular angle for this particular triangle. So again, these are your trigonometric ratios. The representation of certain sides combined with a specific angle. If we change the angle, we can change these ratios. If we change the sides, we could change these ratios, because they're meant to change as the triangle changes and evolves. Tangent, opposite over adjacent, 4 over 3. Now, in things like elementary school and pre-algebra, they would talk about, you gotta simplify fractions. The only thing you need to simplify for this class is fractions that contain radicals in the denominator, which is why your calculator may be helpful. As you might imagine, there will be some problems that produce radicals. If that is the case, the only things you need to simplify are the ones where the radicals are in the denominator. If the top number is bigger than the bottom, leave it. 4 over 3 is acceptable and beautiful. All right?
Okay, how do you...
Good.
All right, so on your phone, that's an O, right?
Mm-hmm.
Okay, so how do you keep that, like, a 0?
Personally, whenever I'm doing the trig stuff, so she asked the question, how do you keep track of whether it's a 0 or an O? Like, is that actually a 4 or is that like a 40? Like, especially if you're writing it all in one color, like if you're writing on your paper and pencil or something, that can be easy to slip up. A long time ago, I trained myself that zeros have a slash in them. Similar to how you see on some calculators, where they'll always put a 0 as this 0. So whenever I write zeros on my personal paper, if I'm writing it all in one color, like if I'm doing it with an ink pen or something, if I'm doing it with a pencil only, you'll see my zeros look really weird all the time. It's because I want to make sure to distinguish them between that and an O. The other thing you can do is instead of putting O, you can just put, like op or opposite. You can just label the whole word, right? I just like giving it a little shorthand just to make sure I don't have to write too much. This is math class, not English class. I don't want to write too much. Okay? Little things like that can really help keep things straight. So those are the big 3 from what you'd have in geometry, right? Let's extend this to more of a trig topic. In trigonometry, we talk about the other 3, the other big 3. Now, there is a relationship between the 3. You'll always see me write it in this form because this helps me to keep track of how I find my solutions. I never memorized a second set of letters to get the second one. I memorized the order they went in, and then afterwards, once I had the order down, just remembered that they were inverses. So this problem, let's put it next to it. We have, in order, cosecant of theta, secant of theta, and cotangent of theta. Remember, these 3 are all just inverses of the first 3. So if you get them at least in the right order, then as long as you know the first 3, Finding the second 3 is just a matter of flipping them over. So if sine is 4 over 5, the cosecant will be 5 over 4. Always the inverse of it. So again, if the sine is 4 over 5, the cosecant will be 5 over 4. If the cosine is 3 over 5, the secant will be 5 over 3. Always the inverse, always the opposite. If the tangent is 4 over 3, the cotangent is its opposite, its inverse, 3 over 4. Providing a nice distinct relationship. What's important to note is that for each pair of sides that you could possibly pick, there are 2 trig functions that could work with it, depending on which one you want to talk about first. If I want to focus on the hypotenuse and the adjacent, I could either think with the cosine function, but I have to put the adjacent first, or I could think with the secant function, and then I have to put the hypotenuse first. This is meant to cover every single possible relationship that could exist between any combination in any order of these sides. These are your 6 trigonometric ratios. This is an example of an easy level problem. You'll have a couple of these in your homework, where they've given you the full triangle and they just say, hey, name your trig ratios. The biggest things I would tell you in preparation for this would be, A, the most commonly missed thing is labeling the sides wrong at the beginning. Labeling the opposite wrong or the adjacent wrong or flipping them is really common. Because if you do that, then you can't possibly get the trig ratios right because you're going to put the wrong ones in the right place. Okay? Second most common thing is to try to overcomplicate this and think it's like some big, terrifying calculator problem that you got to try to type something out in. No. A trig ratio is just a fraction. So I have 6 answers. 4 over 5, 3 over 5, 4 over 3, 5 over 4, 5 over 3, 3 over 4. Those are my 6 trigonometric ratios. I just make sure to keep them in consistency with which trig function they go with. Let's take a look at this one step harder. How could I make this one step harder? Well, we mentioned Pythagorean theorem because it does come up. Let's take a look at what happens if one of these sides is missing. Okay? God bless you. Someone else, sorry. You'll notice for all my problems, I'm going to keep this right-hand side the same because it doesn't change. The 6 trig ratios are the same 6 functions. I'm not going to change that right-hand side. What I'm going to do is I'm going to adjust them based upon the new theta and the new triangle's values. Because that can't change. Sine is always going to be opposite over hypotenuse. The picture can change, the angle can change, the sides can change. That stuff can all change. Sine can't change. It's predefined, it's predetermined, it is known. All right, next one. Theta. Let's say, for example, we have one side that is unknown. Let's make this something interesting. 7, 11, and this unknown, empty, missing side. If you're not comfortable leaving that side blank, I know some people, when they see a problem like this one that asks for the trig ratios, they'll immediately put a variable there. Like they'll put like x there or a there or something. If you want to be one of those people, go for it. It works. Keep in mind though, my process is as follows. I have to have all 3 sides labeled so I can plug in my trig functions. All 3 sides with a value labeled as opposite, adjacent, hypotenuse, plugged into the 3 and 6 basic trig functions. So step 1, when I see this kind of problem is, I know there's a piece missing because it was given to me incomplete. So I'm going to take my first step, which is going to be Pythagorean theorem. Now, if you want to, you can go a little out of order here. Maybe you want to go ahead and label your sides while you start the problem. That way you don't have to think about it later. I often do that. Because I'll come in here and be like, okay, let's label my sides. Because I'm thinking of using this formula, where it has O, A, and H, and I can plug into it easily. So if I label it first, then I can plug into the formula a little easier than having to figure out, okay, which one's A and B? I forget. It doesn't matter, but that's usually a moment of stress. Okay, so let's label those sides. The theta is in the bottom left-hand corner. Remy?
Oh, I was. Yeah.
Okay, sure.
Yeah, because I was starting something first.
Okay. Let's see here. Let's go with Anna. In this picture, of my 3 sides, I have an 11, a 7, and a blank side. Which one's the hypotenuse?
The 11.
That's right. Raina, which one is opposite of theta?
The blank one.
Yes, the blank one.
Yeah.
Good. I'm going to leave it as a little O. Or I could write opposite or op. As long as I know it's the opposite side. You can even use a different letter if you really wanted to. The 7, by process of elimination, it's got to be adjacent. I'm now going to plug into Pythagorean's theorem. I have an unknown. I could use it as a variable. I could just leave it as like O or A or H, whatever one it is. But I need to find that missing value. So next step, I've got them labeled. Let's plug them in. Pythagorean's theorem, the modified version that I choose to use is as follows. O squared plus A squared equals H squared. Very similar, just with the values dictated from Trig. O squared, so that would be O squared. Plus A squared, so plus 7 squared. Equals hypotenuse squared, 11 squared. I will admit, this is a time where Remy is pretty correct here. I will occasionally forget that that's an O instead of a 0. And so you may be like, let's just use a different letter. Let's use X instead or something. Whatever it's going to take to make sure you remember that that's the variable. And that's what I'm trying to solve for. Now at this point in time, this becomes an exercise in pre-algebra stuff. Getting a variable by itself. So let's walk through the steps. Step 1, squaring the numbers.
49, 121.
O squared is O squared. 7 squared is 49. And thank you both for that 121. Fantastic.
Subtract 49.
Subtract the 49. Very nice, Mimi. Very nice. So I end up with O squared is equal to 121 minus 49.
72.
72.
Take the square root.
And I take the square root to get O by itself. So O is equal to the square root of 72. Calculator is helpful here if you can't do it by yourself.
6 square root of 2.
6 square root 2.
Isn't it plus or negative?
Leave it as a radical. Now, Remy, you asked a fantastic question. I'm so glad you did. Is it positive or negative? Now, if I was in Algebra 1 or Algebra 2, I would be yelling at everybody else for not asking that question. We are now in Trig. We are dealing with a triangle. We are pulling this from geometry. And for now, we're going to follow geometry rules which state the sides of a triangle cannot be negative. So, fantastic that you pulled that out. You are correct. When we take a square root, we should always consider the positive and negative. For this specific example, we can reject the negative. Thank you for bringing that up. That's fantastic. Okay, so now I can go back to the original problem and put this 6 square root of 2 back where it belongs. 6 square root 2. And now the rest of this is just a simple matter of plugging and going. Now, if you're the kind of person that likes to simplify as you go, I have a small word of caution that I will dictate at the end. If you're the kind of person that's just like, I'll do all that stuff at the end, you're thinking more like I do. I'll explain why that's actually okay in both cases. Let's take a look at each one, starting with sine. According to our trig list, sine is equivalent to opposite over hypotenuse. On our picture, I've already labeled them, which is great. Opposite over hypotenuse, so for sine, 6 square root 2 over 11. Now, I will not go in order, because I remember these by their relationship to each other. I've got sine done. The next one I'm going to do is cosecant, because they're inverses of each other. If this is 6 square root 2 over 11, then this one has to be 11 over 6 square root 2. Now, mathematically, you're never supposed to run around with the radical down. The radical is never supposed to be in the denominator if you can help it. So one of these will need to be simplified. The other is actually okay. The reason why I recommend simplifying at the end is because if you get to the first one and you have to simplify something, the second part, usually you won't have to. And so I'd rather go ahead and get both and then ask the question of what should I simplify, then start simplifying at the beginning and then have to re-simplify again at the end. It gets really annoying if you do it that way.
That one is going to be 11 square root of 2 over 12.
11 square root 2 over 12. Fantastic. And a calculator's your friend there if you still struggle with some of those radical stuff. Alright, cosine. Like I said, I go out of order than traditional geometry because we have this defined relationship. I can do one and then very quickly get the other one because it's just an inverse. Cosine. What would be my value? My trigonometric ratio for cosine.
Adjacent.
Adjacent over hypotenuse. So for this picture, 7 over 11. And if cosine is 7 over 11, what's that going to make secant?
11 over 7.
11 over 7. This is why I choose to do it in this order. It's not better. It's not worse. I just happen to like doing it because I can get them bam, bam, right in a row. Okay? Tangent. According According to the formula, tangent is opposite over adjacent, cotangent is adjacent over opposite. In your homework, you'll have some problems that ask you for all 6. Some other problems might ask you for a very specific one. It might say, hey, I only want the cotangent one. In that case, you don't have to list all these out. Just get to the one. And maybe you could have done it with what was given to you. Maybe you need to go ahead and find the other missing side. It takes some creativity to be faster at these, but if you go through these steps, you will always be able to find all 6. Tangent?
Is 6 square root of 2 over 7.
Very nice. Cotangent, the first version would just be the flip of it. So 7 over 6 square root 2.
And the other one is 7 square root of 2 over 12.
7 square root 2 over 12. Well done. Very nice. These are the 6 trigonometric ratios. This should be a medium level problem. You got one side missing. We have to use Pythagorean theorem to find it. It's still not too bad though. Notice again the same basic process. Our goal becomes how do we find these missing components and get to a solution using all 6 trigonometric ratios. Let's take a look at a hard one. What could a hard problem possibly look like? How can I make this any harder? You can't be missing 2 sides for good reasons.
You should make it harder like that.
Because Pythagorean theorem only works if you're missing
Then you
1.
can even figure it out.
The only way I can actually make this any harder, say again? Nope, don't even need that. What I could do is to make the numbers nastier. If my sides are nastier numbers, then using Pythagorean theorem to find the missing side could be harder, and that could make it tougher. That's the biggest thing that happens with these kinds of problems, is if I throw a really nasty random number up here, can you take the time to figure out how to write it in terms of these trigonometric ratios? It's not changing the process though. Sine is still going to be opposite over hypotenuse. We can still use Pythagorean theorem as long as we have O, A, and H. What's going to change is if those numbers get nastier, are you still confident in your ability to get to your solution following that same process when it was 3, 4, and 5? Okay? Let's go one level up. Let's see if I can make this real nasty. Like make your mama cry. She might do that anyways. That's not my fault, I promise. Nasty numbers. Nasty numbers. How can I make this nasty? Let's see. Okay. I go here. Right angle there. Theta there. What if I made this number like 8 over 9, and this number like square root of 2? Maybe a little nastier? Maybe. It's not going to change the process though. That's the important thing to always remember about these kinds of problems. You can't possibly change the process here. The process is consistent. The 6 trig ratios don't change. The fact that they're related to very specific sides doesn't change. Theta doesn't change. It could be in a different spot, therefore dictating new opposites and adjacents. But the process will never change. So let's go through that process. Step 1, I'm going to go ahead and label my sides, because that's my traditional first step, no matter what. I want to make sure to get all the sides correct while I'm still fresh, before I've tried to go through and find any missing side using Pythagorean theorem. I'm going to go ahead and label my pieces. Let's see here. Michael, which side's the hypotenuse?
Be the blank side.
Blank side, yes. Let's see here. Hannah, which side would be adjacent to theta?
8 ninths.
8 ninths. Do that with an A. All right, and Hannah, which side would be opposite? Oh my gosh!
Oh, Hannah, twice?
She was looking pretty nervous over there, though.
It's not my fault, I promise. It's been a long day.
Which side is what?
The opposite.
Square root of 2.
Thank you, Haley. I'm sorry, that's twice this week. You get one free yelling at me session.
Wait, why
You wrote your A's.
Yeah, you don't pick up.
What are you doing?
I'm so focused on getting the name right, I just can't even get a letter right. What the heck?
I was confused.
I blame Andrew. It's all his fault. Andrew, it's your fault. Okay. We got a missing side. Let's throw Pythagorean theorem up here with the correct components and make sure it's in the correct order. If you mess up putting the things into Pythagorean theorem, you will get a different solution than you're supposed to. So make sure to note I do OA and H first and then use OA and H in Pythagorean's theorem so that I have less chance of making a mistake. That's the only reason I write the alternative form is because I make fewer mistakes when I write it that way. Well, fewer than what I've done so far today anyways. All right, let's throw it up here. Pythagorean theorem states, according to the trig version, O squared plus A squared equals H squared. O squared, square root of 2, squared, plus A squared, A over 9, squared, equals H squared. I start simplifying. Some of these you can do with the calculator, some you can do without, some may require both. Depends on the problem. Square root of 2, squared. 2. Remember, squared and square roots always cancel. 8 over 9, squared. That's right. 64 over 81 equals H squared. Okay, may need some assistance here. How do I add 2 and 64 over 81 together? I want to get this down to one fraction so I can take that square root better. Suggestions?
4 plus 1.
Multiply by 1 over
62.
81.
You want to do 81 over 81.
81 over 81?
Yeah, so you do like 81 over 81. That way you're multiplying it by the number 1. So this will become 162 over 81 plus 64 over 81 equals H squared. Because remember, you're allowed to multiply anything by 1 without changing the number itself. 162 divided by 81 is still 2. Now I can put those two together. 162 over 81 plus 64 over 81. Remember, when you add fractions, the bottom stays the same. 81. It is the top that changes. 326. Yes, thank you.
226.
226. 226. Okay, can we? Try it. I'm going to go ahead and square root both sides because I'm not sure. I can always simplify afterwards if I need to. If I square root both sides, I'll end up with H. H equals the square root of 226 over 81. Does that simplify at all?
It's 226 over 9.
Yeah.
So you get the square root of 226 over 9. So that piece is kind of nasty, but we'll make it work. Okay? Like I said, the only way this can get any harder is if your numbers aren't as nice. That does not change the process, though. It just figures out how to put those into our fractions and then get to a result. Let's go back now. We're going to go back to the original problem. We now have H. H is the square root of 226 over 9. Let's plug in our 6 trig functions. Got a moment left. Let's do it. Sine.
Square root of 2 over 226 over 9.
Square root of 2. Big fraction bar over. Square root of 226 over 9. That would probably simplify somehow. Calculator is beneficial there. I'll leave that for you to do. So we're running out of time here. Cosine would be 8 over 9 divided by square root of 226 over 9. Again, I'll leave that one for you to do on your own. It's just simplifying fractions. Calculator would be very beneficial. Tangent. Square root of 2 over 8 over 9. And then, of course, cosecant, secant, and cotangent will be flipped versions of these. So, square root 226 over 9 divided by the square root of 2. So, square root 226 over 9 divided by 8 over 9. And the last one, 8 over 9 divided by the square root of 2. These will be our 6 solutions when fully simplified. We'll be looking at some more of these tomorrow, as well as a couple of other formulas we will need, but that is it for today. Have a good rest of the day.